Okay, so here's example 2, and I'll see how long this goes, but I'm already looking at example 2 and example 3, and I want you to pay attention. It's the same image, and that's on purpose, because whether this image represents velocity versus position, your answers and what you're looking at and where you're looking at them is going to be different. So again, like I preferenced in the first video, what you're looking at matters. So in this case, it's position. So this represents the position. Again, thinking about maybe something moving along the x-axis, I'm only keeping track as where is it at? Position 1, 2, 3, 4, 5 on the number line. Okay, so when I think about this as being position, and I want to know how many times does it change directions, well, going back from the last example, you have to not just have a zero velocity, you have to change signs. Your velocity has to change from positive to negative or negative to positive. And if you're analyzing a position graph and you want to know the velocity, and remember velocities change in position, instantaneous rate of change, the slope of the tangent line, aha, there it is, slope. The slope of a position function represents velocity. So I'm looking for where are there changes in slope? Where are the slopes going from positive to negative or the negative to positive? So how many times does a particle change directions? That translates to, okay, how many times does the slope change? Well, here I have a zero slope, and here I have a negative slope. I technically haven't changed signs. 0 to negative is not good enough. I actually have to go negative to positive. So here's a negative slope, so that's a negative derivative. Here's a positive slope. So at this instant here, I change directions. And here, I change directions. So that it changes directions 2 times, okay? But the thing is, this is where math is going to separate a little bit from physics, because you guys already probably figured this out. That's a cusp, and that's a cusp. And it's not differentiable at that point. So clearly, this position function cannot represent something that really happens in our physical world. So surprise to surprise, spoiler alert, this is just something to help us start looking at graphs as if it were position. How would you interpret that? But this physically can't happen. You can't go from having a velocity of -2 to instantly having a velocity of +2 in this world. It would have to be smooth. It would have to transition. So this clearly doesn't represent what can happen in our physical model. That's okay, because it's not physics. So we can say, oh, if it could, what would you do? And then we get math. So that's nice. Okay, so 2 times. One's here and one's here. Okay, so and then in terms of if this slope, and it's just linear, so it's easy to calculate. If it was quadratic, we would have to estimate it. So right now it's okay, it's linear. But now if we want to know when's it moving to the left, well, left associates with velocity. Velocity is a direction. Velocity is the slope of these lines. So when do we have negative slope? We have negative slope here, here, and here. Those intervals have negative slope. Therefore, they have negative velocity. Therefore, we would equate them as moving to the left. So what is that? T equals 2 to 4. And then, let's see, 5, 6, 7 to 10. So I can say like T from 2 to 4 and from 7 to 10. Open interval strictly because technically the velocity at these cusps is undefined. Okay? What is the velocity when the object is at time equals 3? 1, 2, 3. So I'm sitting on the x-axis at the position, but it's still part of this negative slope. So -2 units per time. Does it give us a dimension? No. 10 seconds, so we could say like centimeters per second. You know, if they don't give you units, then it's okay not to give units back. But if they do give you units, obviously you want to follow this. So we say -2, for lack of generality, centimeters per second. Okay, what's the acceleration at time equals 2? Time equals 2, well, let's see, time equals 2, well, you're at a cusp, right? So the first derivative is undefined. And then if the first derivative is undefined, because you can't take you can't take a tangent, then your second derivative would also be undefined. But let's say, for instance, that this was meant to be not at time equals 2. Let's override that and call it time equals 3. And I'll have to make sure I make a little mental note to update the 2020 version of this workbook. Let's say this at t equals 3. Now what's the acceleration? Well, the velocity is -2. Like we just calculated that. And acceleration is the change of velocity. Well, the thing is, if this is linear, the velocity is constantly -2. So what's the change of the velocity at any point on this interval? It's not changing. So the velocity is constant, therefore its acceleration will be 0. So 0 centimeters per second, or per second squared. Okay. And then it says, what's the average velocity of the object over 10-second interval? What is the average speed? Well, so again, maybe if you're not familiar with those definitions, take a look at the page, I think I said 37, where it gives you, again, a definition of those two things. Oh, that's not part. So, given a position graph, okay, so, so here we go. Okay, average velocity. Average velocity is displacement over time. This value may be positive, negative, or 0. Average speed is total distance over time. This is always non-negative. So you're like, okay, well, how do you find displacement? So you go back up and say, okay, oops. How do you find displacement? Displacement is the difference between the final position and the initial position. So what is that, like, what is that difference? If you end up left of your starting point, you could have a negative value. So we take a look at our graph. The final position is at 0. The initial position is at 2. Because remember, these y values are representing position. So the y value here, the final position is 0. The initial position is 2. So if I'm looking for displacement first, so I'll do this, displacement. So that would be final position, which is 0, minus initial position 2, over your time, which was 10 seconds. So this gives me -1/5 centimeters per second. That is my average velocity. And again, that can be negative. Okay, so average velocity can be negative. It's the final position minus the starting position over the time. So -1/5 centimeters per second. Now, average speed. Now I don't really care if I'm going forwards or backwards. Negative doesn't matter. So I sort of have to interpret this graph thinking, okay, I'm at position 2. Right, let me erase this. Okay, so I'm at position 2, and I'm just holding. I'm holding. Now I'm doing some movement. I'm going to position 1, to position 0, to position -1, to position -2. So I've traveled 4 units of space. And then I'm going back up to position 1, position 0, position 1, 2, 3, 4. So this interval, I went from -2 up to 4. That's 6 units of space. Here, 4 down to 0, that's 4 units of space. So again, I traveled 4 units in this direction, and even though it's a negative direction, distance doesn't matter, only if it were displacement. This right here, I've gone up 6 in that direction, and then this I've gone down 4. Oh yeah, so I started to, right. So if I think about, okay, I've traveled 4 this way, and 6 this way, that's 10, and then 4 more this way, 14. So I've gone 14 total units. 14 total units over the interval of 10 seconds. So for my average speed, it's total distance over time. So do a little bit of calculation. So that was 14 over 10, or 1.4 centimeters per second. And remember, like, we're visually seeing position being measured, and its measurement is in this direction, right? It's the label of our y-axis. But remember, we're representing something moving in this direction. So it gets really confusing because we're keeping track of how much did it move this way, but we're graphing them, right, on the y-axis, okay? So that is our displacement versus our time. Okay, so I think I'm gonna pause this and do one more video for example 3.